Okay, we are recording. So today we speak about damping. In order to make an example, so we can focus on something that maybe some of you already saw in the city. The Isozaki building, the tower that is the top height tower of Milano, has 4 legs like those. And the purpose of that is to damp the movement of the tower with respect to the wind. Then there are also an architectural plan. So the architect, he didn't like the legs. Someone else didn't like it because it looks like the building needs the legs in order to stay. I'm stopping here, that there is a sound. All right, it is better? No. All right. So the legs of the Isozaki, now they have the purpose of damping the motion of the building due to the wind. There is also another option. Usually there is no buildings around the world with devices like that. Usually what is happening is that on the top of the building there is a mass, and this mass can move or more than one mass. So there is a system that is a spring together with a damper that is connecting the mass to the building, so that the mass can oscillate with respect of the building. And of course it is tuned on the frequency of the building that should be damped. That typically is the first mode of vibration. And so usually the tall buildings that can be excited by the wind, like Isozaki building, almost always have inside the tune mass damper that is taking care of increasing the damping of the building, so that the vortex shedding excitation of the building is not making seasick the people who are living into the building. All right. And here instead, there is a device that is made like that. It is not very efficient, because you can understand that if there is a movement, yes, I have an elongation of this of the length that is between this connection and the connection into the tower. But the movement here goes in this direction, all right? And so the damper should be much more effective if it was positioned like that. Okay, but we cannot position a damper in the middle of the sky, and so we cannot do it. And so if you want to bring something to the ground, you have to bring it down. And if you are connecting to something that is here, the building is not moving here. The modal amplitude close to the connection is almost negligible. In order to make the device effective, it is necessary to make the connection in a position where the work, that the force, speaking with the correct words. So what we need? We need that the action given by the damper is able to make a lot of work on the mode, on the modal display, on the mode displacement into the local modal displacement of the point in which it is connected. And so it will be very effective if it is positioned in a location that is moving a lot within the mode. And so the modal shape close to the connection is totally not effective. If I am positioning a damper down here, it is absolutely wasteless. Okay. So there is a connection here, so then there is a device, and this device is bringing the movement to a damper. And but then there is also a spring. There is a spring because you can understand that the movement can be a small movement, and so if there is a clearance among the different connections, you could have a small movement that is not transmitted into the damper itself, and so the idea is that all the clearances must be kept in the same direction with a spring that is pushing the devices in order that there is that you never have an inversion of the force that is making a movement that is not totally related to the movement of the building, because you can have a how do you say, gioco, a clearance among the different connections. Anyway, so there is a device like that. And so the point is in which way we can connect the damping effect of this damper to the modal effect, to the way in which the mode of vibration is damped. What we are addressing today is the possibility, how the methodology with which we can do all of that. In order to do this, first of all, we have to speak about the damper. I think that you should know what we mean about damper. A damper is a device that is responding with a force to a velocity. So the symbology, we are representing the damper in this way. If we are moving with a velocity that is shown here, and I repeat, delta L y dot. So delta L y dot is the time derivative of the variation of length of the damper, all right? And so the force that is able to give this device is proportional to a constant to the velocity of elongation. So our focus is to say, I want to link the velocity of elongation of the damper with the general movement of the damper. But then we go back and we say that the location where is acting this force is reversed. So when there is positive the velocity of elongation, I have to pull the damper up. And the effect of that is a force that is taking down the object. And so that if I am writing the power that is getting into the body is so the force on the body is Rj delta Lj dot minus. Then the velocity is delta Lj plus the product of this makes a negative power. So I have a negative power that is getting into the object, and so it is dissipating energy. Then, in order to work with the dampers, we are making reference to a quantity that is not energy, but it is what we call the dissipative function. So if I am speaking about a damper like that, and I am representing the elongation velocity with delta Lj dot, I name dissipative function the quantity that is 1/2 Rj delta Lj squared. Then delta Lj, you can understand, is linked to the movement. Is linked to the movement through the kinematic relationship, to the kinematic properties of the mechanism, down here, sometimes, if you have the mechanism, or it is linked to the modal behavior of the system. So the modal behavior of the system is stating how much is increasing delta Lj when the specific mode of vibration we are speaking about is moved by the principal coordinate that is driving it, all right? And so let's say that what is happening is that we write delta Lj equal delta Lj Q, where Q is the vector of the principal coordinate of the object. For which reason we are working with this quantity? We do not develop the full theory, and because it is not necessary. So we make an analogy with what is happening to the spring. The force on the spring is written as Kj delta Lj. But if we are working with the potential energy and we write potential energy equal minus 1/2 K delta Lj square, then it happens that dV I use the same symbology that I used in the, sorry. We are using the elongation later now. So we connect, we forget now to speak about the elongation. The elongation is coming later. Now we are connecting the damper and the spring directly to the variable. The variable is the displacement. The variable is the displacement of the connection point in the direction of the elongation, and the velocity of the point, extremity point in the direction of the elongation. And we write the potential energy with respect to the variable, where the variable is the coordinate y that we are moving, that is moving the extremity of the spring. So if we write the derivative with respect of the coordinate y of the potential energy, we are actually getting the force, all right? If we are using this dissipative function, it is in the same way, the derivative with respect of y dot is making again back the dissipation force, all right? So we are writing the dissipation force, and we are writing the force made by the damper, as well as we are writing the force made by the spring, taking the derivative in the case of the spring with respect of the variable displacement, in the case of the damper, taking the derivative with respect of the velocity of the variable itself, all right? So we keep in mind that with the dissipative function, the dissipative function is working in a very similar way as it is for the potential energy, and we work with an analogy, and we develop a little bit of mathematics in order to make the general description of the way in which the system, we can write for the system the connection among the modal displacement of the system and the effect of the dampers that are positioned within the system. All right. But first of all, so we leave it here. So I didn't want to I'm sorry, but I didn't want to work directly into the formulas. What I prefer to do was something different. So I go back a little bit, and I go back to this. So the final goal of everything is to write, finally, a problem that is a problem in principal coordinate. And we already know that the problem in principal coordinate is a diagonal mass matrix, a diagonal stiffness matrix, and we don't know what happens about the damping, all right? So I am starting back, so I am leaving here the question of the dissipative function. It is a detail, we are going to this detail, but first I want to focus on the final results, otherwise we are losing the goal of everything. And so our goal is to work in principal coordinate and to figure out in which way we can write the matrix of modal damping of the system, all right? So here, what we do is opening in two different directions. In case we are speaking about the distributed damping that is intrinsically into, for example, a tensioned cable or a tensioned beam or a beam that is vibrating through bending. So the intrinsic distributed damping of those systems are somehow associated to the mass distribution, are somehow associated to the stiffness distribution, so that although we do not have a modeling of the intrinsic distributed damping, we are building a simple and modeling of that makes an evidence of a link among the distributed mass, the distributed stiffness, and the distributed damping. So that finally it happens, there is an evidence, a practical evidence, that whenever we have the effect of damping because of something that is distributed into the material, then it happens that the damping matrix in principal coordinate keeps being diagonal, all right? But in a case where we are positioning a damper here, and this is the location xj, and this is rj, all right? So we have a damper exactly in this location. And so we have a mode of vibration that is doing like that, another mode of vibration that is doing like that. So we have one mode, another mode. Then what is happening is that there is the evidence that the local concentrated damper is making something different, is making the coupling of the modes. So there is evidence, and this evidence comes also from the discussion that we were starting to do here, and that we are going to do. But it happens that the concentrated damper is coupling the modes. In my opinion, could be interesting to have an intuitive evidence of that can be proposed in this way. So let's think to write the equation of the first mode of vibration. We know that we write the modal mass of the first mode, the modal stiffness of the first mode. This is the principal coordinate, second order derivative, zero order derivative. And then we have to write the work of the external forces due to the virtual displacement associated to the first mode. And so, which is the external forces that is acting? So the velocity at the location xj is the second mode, phi2. I should write phi2 xj. Phi2, the second mode at the location xj, weighted by the velocity q dot 2 function of time. Okay, so this is the displacement is the elongation of the damper is the displacement of this point, and the force is minus rj multiplied by the velocity of the elongation of the mass. now I have to write the work. In order to write the work, delta L is equal to minus Rj phi2 xj q dot 2 time multiplied by, now it depends. It depends on the mode 1. So in order to write the work associated to a virtual displacement of the first coordinate, I have to say that the virtual displacement of the first coordinate is phi1 function of xj multiplied delta q1. So this object here is the virtual displacement at the location of the damper associated to the first mode of vibration due to the virtual variation, infinitesimal variation of the principal coordinate q1. And so the quantity dl over dq1, so the work, the Lagrangian component of the external forces associated to the infinitesimal displacement of the first mode is making a work that is equal minus Rj phi 2 xj phi 1 xj q dot 2 function of time. We know that is function of time. All right, so I divided dl over dq1, and so this quantity goes in the other side and is telling us that we do have also a contribution here associated to q2 dot. Of course, we also have the contribution due to the force that we have here because of the velocity, a possible movement of the mode 1. So together with in the general motion of the system is moving because all the coordinates are moving. And I have a velocity here, not just because the second mode is running with a velocity q dot 2. But I also have that I have velocity because the system is generally moving. And for example, I have that I can have excited the first mode. And so I can repeat all of that, saying that due to the movement of the first mode, I have minus Rj phi 1 function of xj q dot 1 multiplied now phi 1 xj delta q1, all right? But so what does it mean? It means that into here I will have quantity plus Rj phi 2 phi 1 xj square q1 dot plus Rj phi 2 xj phi 1 xj q dot 2 and so on. I would like that this is clear and this is more important than all the theory. If you didn't understand, I need a question from you. Is it everything clear? Yes or no? No. So let's try to understand in which way we are writing all of that. So I don't go into the point of how we do write this part of the problem and this part of the problem because it is the story of the previous lessons. Now we are saying I have a damper that is positioned here. How do I deal with that? This object is making a force. This force is something that is absolutely simple. It's a force that is proportional to the velocity. Okay? The force then this is the force that is acting on the body. Okay? I write minus R J y dot, and this is minus is the force that is acting on the body. So it is reversed with respect of that. So the force is simple, is associated to the velocity, all right? And so I have to answer to the question, which is the velocity here? The velocity here is the superposition of all the modes that are running together. So when I am giving the free motion of the system is moving according to all the principal coordinates that can vibrate. So the general motion of the system, the general free motion of the system is associated to the superposition of all the natural modes. Each of them is vibrating, moved by its own coordinate. And so the velocity y xj time is equal to if I am stopping and at the n principal coordinate, the velocity is this one. The displacement, of course, is y xj time is equal so we write the problem in principal coordinate always, and so the displacement of the general xj location is given by phi q. So this is our way of writing now. So we write that everything is represented in principal coordinate. So everything is represented using a set of new coordinates that are moving the model shapes. And whatever possible movement of the system is represented like that. We can do it. And if we do like that, and it is possible to do, everything is represented in a very physical way and in the simplest way that we can do in order to do the dynamics. But then we must be consequent. And so this is the displacement and this is the velocity. And so I have velocity here, and so I have force here because it's moving the first mode, but also because it's moving also the second mode, and also because all the other modes are moving. Not just because it is moving the first mode, all right? And so when I have to write I can write the effect of this damper as a very generic force that is treated by virtual work associated to a virtual displacement. Virtual work associated to the virtual displacement of the first coordinate, because here I am writing the equation 1. When I am writing the equation 1, I am taking the derivative of the potential energy, of the kinetic energy, of the virtual work, all by the first. Then I write the second equation and I take the derivative by the second coordinate. When we write the Lagrange equation derivative with respect of Q dot kinetic energy and then we say transposed. What do we mean? We mean that we do the derivative of the energetic scalar function with respect of the first. This is a vector. And we write the first piece of the first equation. Then I have the other piece, derivative V with respect of Q, vector transposed. I work with the first and I'm writing the first equation. Then we are writing the first equation also for the damper. For the damper, I am taking the derivative with respect of the Q1 of the virtual work associated to the forces that are acting, and the forces are given by the elongation velocity associated to all the modes altogether, and we take the derivative with respect of the work done by the virtual displacement where I am moving just Q1. And so I am doing like that. So the way in which we write those things that I mentioned is, this is the force associated to the velocity due to the excitation of the second mode that is running, and this is the projection. It is the projection over the first principal coordinate. It is the scalar product, the scalar product. Then I have velocity because also I have a velocity because there is the movement of the first mode. Velocity because of the first mode. And so I have a contribution. And so the contribution will be first, this is phi1, phi1, phi1 square at the location, Q1. But then I have the coupling term. What does it mean, coupling? It means that into the equation here, where I was supposing to have just the coordinate Q1, M1 star Q1 two dots, R star 1 Q1 dot, K1 star Q1. And so in my idea, I had, all right, in principal coordinate, everything is diagonal. And so the first equation maybe was just M star 1 Q1 Q dots plus R star 1 Q1 dot plus K star 1 Q1 equal the work of other forces. Instead, we have also all the others. We have all of them. All of them unless maybe if I am positioning the damper over here, or if in the location where I have the damper, I have a mode that is passing over here. And so if I am in a nodal location, I do not have velocity. And so someone could disappear. But it is a peculiar situation. Usually it doesn't disappear. All right? And so if we are working with something that is extremely simple, that is the damper, and we apply the theory and we try to figure out what could happen, we very surprisingly, we find out that the concentrated damper is coupling the modes. Then, the dual example. But for which reasons the modes usually are not coupled? So for which reason it happens that working in principal coordinates, magically, everything is resulting uncoupled. Let's try to make the similar development of theory somehow with respect to forces down here associated to what is distributed. All right, let's try. I'm canceling here. So let's say that what is happening is that in order to speak of the distributed damping, first we have to speak about the distributed inertia. So I prefer to do like that. I prefer to try to explain for which reason, to try to explain with a direct example here, that writing the forces associated to the inertial action, the distributed inertial action, and writing the contribution of those distributed inertial action into the work done by virtual displacement, it happens that all the out-of-diagonal terms are disappearing, and we have just the diagonal term that is writing the modal mass. So let's say that, and so we are not speaking about damping, we are speaking about distributed mass. But then the movement from distributed mass and the distributed damping will be simply to say that we say that the contribution into the distributed damping is something that is alpha m star. So let's say that we are assuming that the modal damping is proportional to the modal mass. So we are making a similitude, and we do not go in more details like that. So let's make the example on the distributed mass, and then we understand and we have an intuition of the distributed damping. So I have excitation of the modes. I have excitation of the second mode. The second mode is running. It has acceleration. I have a distribution of accelerated forces along the structure that are going like that. This is the second mode. Those are the accelerated forces. We have to reverse because we have to write that if this is the acceleration, the forces are minus, but don't mind. So this is the acceleration, the distribution of the acceleration, and the distribution of the inertial forces is this one, but reversed. And it has the shape of the second mode, and it is scaled by the derivative, the second order derivative of the second principal coordinate, all right? All right. And I have to say dx. So this is what happens for an infinitesimal length. Now, in order to write the work of this distribution of force through the virtual displacement of the first mode, I have to do exactly the same that I did here. So I have to say that I have a virtual displacement of the system that goes with the first coordinate. This is the virtual display, sorry. So the virtual display, I cancel. So the virtual displacement was this quantity here, all right? And so I have to say that this distribution of inertial force has to work with a distribution of displacement that is the shape of the first mode. And so it is, I have to say, phi1 function of x multiplied delta q1. So I have to make the scalar product among the distribution of force, the distribution of displacement, and then I have to integrate from 0 to L. All right. If I have to work with the effect of the first mode, so if I have to work with the first mode, and if I have to make exactly the same procedure for the first mode, I should have written the same thing. So integral 0L m function of x, phi1 function of x, q1 two dots, and then phi1 function of x delta q1, and here dx. So I pretend that you understand that phi1 delta q1 is the virtual displacement associated to the virtual movement of the first coordinate. I want to write the first equation. And so I am giving a virtual displacement to the system along the first coordinate. And then I write the effect of that, the way in which all of that makes work associated to all the forces that are distributed. And so the distribution of mass, the distribution of in inertial forces writes for the first mode an effect that is phi1 multiplied phi1, so phi1 square, mass phi1 square, integrated over dx, that is actually m star 1, all right? M star 1, all right? And so I am writing the model mass. So I am saying that the procedure to write the effect of a distributed action that is proportional to the movement in this way, for example, for the mass, makes something that is written in this way, and for the second mode, it is making exactly the same, but so this Q2 two dots goes out from the integral. We don't care, goes out from the integral. It goes out from the integral, all right? But into the integral, I will have phi2 function of x times phi1 function of x. And so I have this, the integral of this shape through this shape weighted by the mass distribution, and for the orthogonality property, this is 0. So I tried to help you to understand that we are writing the effect of those distributed forces through the principle of virtual work, and all of that is making the distributed action be weighted by the distributed displacement associated to the coordinate with respect to which we are writing the equation, all right? And so, of course, if it is 1, 1, we have the first modal mass. But if we are working with the displacement of the first mode, virtual displacement of the first mode over the distributed force, inertial force associated to the second, I go in the direction of writing the integral distribution of mass, one shape, the other shape. So the shape 2 times shape 1. And so the reason why I get the diagonal matrix into the effect of the inertial forces is because the inertial force is equal to the displacement, just it is scaled by omega squared. The shape is not changing. All right? And then, if I am working with the second, with the coordinate that is, if I am making the virtual displacement of the first over the distribution force of the second, I make the two modes working together and taking the integral of the distribution of the mass times the shape of the first with the shape of the second. It is not when here we are acting with a damper that is acting in one single place and we are just making the scalar product of this displacement mode 2, this displacement mode 1, they are different and not equal to 0, 1, and so they're not disappearing. So it is disappearing because we are integrating the distribution of mass through the distribution of shape of mode 1, distribution of shape of mode 2. Where is the damping? The damping is just constraint in saying that we are assuming that the distributed the dissipations associated to distributed internal action in the material is proportional to the mass, distributed mass, and is proportional to the distributed stiffness. So you could imagine that where you have a lot of mass, you have a lot of material, and so you have more dissipation. If the dissipation is proportional to the volume, for example, or to the mass, you have more dissipation because you have more mass. And so it is not stupid to make the hypothesis that as much as material I have, as much as dissipation I have. If I have to bend a lot of material, I'm dissipating more than if I am bending a small piece of material. And if I have a location where there is a lot of stiffness and I am moving all of that, again, it's the same thing. And so there is this very simple hypothesis that is anyway reasonable to say that the distributed damping actions are somehow proportional to the mass distribution, somehow proportional to the stiffness distribution, and so that it happens that making the calculation in the way that we did, it becomes obvious that it becomes, let's say, reasonable to justify what is appearing in the real life. In the real life, with the system where you do not have concentrated large dampers, but just distributed damping that is associated to the material that is in a dissipative action internally, the modes are separated, are not coupling. And so there is an evidence. There is an evidence that the modes are not coupling each other due to the intrinsic distributed damping. And so that from this evidence, Mr. Taylor said, all right, we make this a very nice hypothesis, and the very nice hypothesis is to say that I have a system that was modeled through n finite elements or whatever, n degree of freedom. I have a mass, M, mass matrix. I have a stiffness matrix. And then this mass matrix could be also the M star matrix diagonal of the continuum, or the K star diagonal matrix of the continuum, all right? And the rule, the proposal is, all right, we say that we can adopt a damping matrix that is written as a linear combination of the mass matrix and the stiffness matrix. And here for the continuum, we say R star is diagonal and is equal to alpha plus beta, where alpha and beta are the two numbers that are stating which is the way in which we are modeling the modal damping in the continuum, or the distributed damping in the n degree of freedom. So if you have an n degree of freedom system, so I would underline that here you have a system with a huge number of free coordinates. You made a finite element code with thousands of coordinates. And so you calculated those mass matrix, those stiffness matrix. And so you would like to stay in those free coordinates and you would like to work with a damping matrix written in those coordinates, but that is making you sure that if you are moving through principal coordinate, this matrix of damping is not coupling the modes. If you make an hypothesis like that, you are totally sure that being the damping matrix proportional to the mass matrix and to the stiffness matrices, as those are, let's say, made diagonal by the transformation in principal coordinate, you are sure that with this modeling, you will get a diagonal matrix in principal coordinate. All right, so I spoke on the two sides. The n degree of freedom, where you say, I have a full matrix of mass, a full matrix of stiffness, and then I get a full matrix of damp. And then I say, in principal coordinate, in the continuum, we have a diagonal model mass and diagonal model stiffness. And we say, with the same rule, all right, diagonal damping matrix equal to alpha mass matrix, beta stiffness matrix. It is the same. It is the same, all right. But the idea is that with this modeling, you keep the property of being diagonal, the damping matrix, because you are associating the mechanism of defining the work associated to a virtual displacement in one mode and associated to the distribution of the damping effects on another mode, but you are working with something that has the mathematics that is totally equal to what you did for working for the stiffness and for the mass itself. And so this is the very general idea. I would like that you have the vision that the concentrated damper is coupling the modes made by this going into the details of the way in which we are writing the work associated to a virtual displacement and taking the derivative of this work with respect of the variation of the coordinate and making it work with the actual force that we have here that is associated to another mode that is running and looking at what is happening that we are coupling the two things. Now we can write the mathematics of all of that. That is making the final representation of everything in a very simple way, but that is out from the possibility, in my opinion, to understand the real reasons because all of that is happening. So the reason of having spent all this time was to understand the distribution of inertial forces in mode 2, that is making work with the virtual displacement associated to the first mode in order to look at the possibility to have an out of diagonal term m star 1, 2, where the answer is not. Not because we write and we have phi2, phi1, m distribution, and all right, this is the error. All right. But we made all of that with the physics of the distribution of inertial force and with the physics of distribution of virtual displacement and calculating all of that with something that was very simple. And the same for the virtual work associated to that. I hope that this is, in my opinion, more important than making the calculations with matrices and whatever that then becomes a mechanical exercise, and that's it. But now we do it. So we go back to this story of the dissipative function. So potential energy, the force is written as derivative of the potential energy with respect of the moving coordinate. Dissipative function, the force is obtained through the derivative with respect of the coordinate of the quantity velocity y dot of the dissipative function. So let's keep in mind that there is this association, all right? And then we write the problem in full generalities. Okay. So here we have to understand that the elongation of the damper generally is associated to the mechanism, and then is associated also to the shape. But then we have the very simple case here where the delta Lj of the damper is just associated with the mod shape. So this case here, that is very simple. Here we have y, function of x time. This is x. The elongation of the damper is simply written here as the modal shapes calculated at the location phi j, multiplying the principal coordinate. That's it. And the velocity of elongation is, again, the modal shapes multiplied by the derivative with respect of time of the principal coordinate. But generally speaking, we could have the mechanisms into here. And so we should write that there is a relationship, a functional relationship among those quantity and this quantity. The functional relationship is the kinematics of the mechanism. So there are some other functions, not just the modal shape multiplying the principal coordinate, but something else also. And so the general way in which we are writing all of that is to say that the elongation is a function of function of time through the intermediate free coordinate that are the principal coordinate, and then taking the derivative with respect of time, I have to multiply all of that times the derivative with respect of time of the principal coordinate itself. All right? In this quantity, d delta L over dq, that is generally speaking, what is taking into the mathematics of the mechanism, in the very simple case that we are dealing with here, is simply phi vector calculated xj q dot time. And here I have to say transposed. Is it clear? So the derivative with respect of q of this quantity makes the modal shapes. All right. So so I take the derivative with respect of q1, I have phi1. The derivative with respect of q2, I have q2. With q2, I have phi2, and so on. All right. And so we can write like that. So All right, in the similar way that we did for calculating the kinetic energy and potential energy, we write that the quantity delta Lj square is the square of this quantity here, but this quantity is this object here is the scalar eta, okay? The square of that, so the transpose of the scalar is still the scalar, and so it's writing the square of this quantity, we write eta transpose multiplied eta. And so all of that makes Q All right, so the quantity eta is phi transposed Q dot. And this is a vector, this is a vector. All right, eta transposed is Q dot transposed phi. And so the quantity dissipative function is written as so with this representation, I say that this vector column is multiplying this vector that is rho. Those are the vector of the modal shapes calculated at the location of the damper, the same here. And so at the generic collocation ij, I have the element that is phi I xj, phi j, xj. Or maybe I say rs. Probably in order not to confuse with the I and j that is running here. And so in the generic location of, so I write the dissipative function as a scalar that is made by a matrix. In this matrix, there is the products of the different modes, 1, 1, 1, 2, 1, 3, 1, n, and then go on, 2, 1, n, 1, and so on, multiplied by this vector. So this is n, this dimension is n, this dimension is n, where n are the number of modes that we calculate. It is possible to show with full generality that if we write the Lagrange equation equal Q1, Q2, Qn, the virtual work of the external forces, all right, the way in which we can write the virtual work of the external forces that are the forces arriving here at the location xj associated to the movement of all the coordinates. So it is possible to show in full generality that given this magical function, that is the dissipative function that is written in this way, so the damper quantity, the velocity, the square of the elongation velocity of the damper itself, into here is plenty of kinematics relationship together with the modal shapes also. In case we do not have the kinematics, we just have the modal shapes because the movement is just associated with the modal shapes. This helps us in order to make it very clear. I hope that this is very clear, that the displacement here is the amplitude of the modal shape at the location xj. Finished, all right? And so the kinematics is simple 1. The kinematics is represented by 1, all right? So we build the dissipative function that is extremely simple. In case we have many dampers, we have the summatory of dj. So if I have 2 dampers, I will have another object like that. Or if I have many dampers, I have many objects like that. It is additive. It is additive, all right? But all of them are behaving exactly the same. Then it is possible to demonstrate with full generality that the virtual work of those external forces is simply written as minus derivative of the dissipative function with respect of the vector q dot transposed. What does it mean, transposed? It means that the derivative with respect of the vector is a row, and instead we write in columns. And so in the first row we will have derivative with respect of q1, derivative with respect of q2, and so on, all right? Then, in the same way that it was done, and it was somehow a bit demonstrated for the mass matrix and the stiffness matrices that are coming from the kinetic energy and the potential energy, this derivative with respect of the vector q dot, in case the function, energetic function, is a quadratic form like that, and we made somehow a little bit of a demonstration, an intuitive demonstration, the derivative with respect of that, considering the hypothesis that this matrix here is symmetrical, and it is symmetrical, because it is clear that so the way in which we built makes so that it is symmetrical, is simply the matrix itself multiplied by the vector q dot. It is like saying that you have dissipative function equal 1/2 rj y square dot is equal to so the derivative d su d y dot is equal to 1/2 rj y dot plus 1/2 yj rj equal rj y dot. All right. In case we have one single coordinate y, and the elongation is the displacement itself. So if we have this system here, the mass that is made here, all right, and this is the displacement y, okay, and this is rj. We write a dissipative function of this, and the force is represented by the derivative of that with respect of q dot, and it is, okay? So we make it very complicated in order to say something that is very simple, but in case you have 100 modes to take care about, is very much work. So I wrote this in order to say that is exactly what happens in the 1 degree of freedom, but here we have n degree of freedom, and so that we have to write in a matrix form, but the theory, the concepts are always the same. And so finally, we discovered what we calculated at the very beginning, So we discovered that for the first equation, we will write something like that, where all right? So we discovered that in case we are positioning the damper here, and those are the shape of the modes, we are building a problem where in the equation 1, there is the contribution of Q dot 2, Q dot 3, whatever, Q dot n. And so it means that if I am giving an initial condition where I have, for example, the mode n, just the mode n, then when the mode is moving, this Q dot n is making noise into here, and it is exciting the mode 1. And so it happens that it will not happen that I give an initial displacement along one single mode, and the system go ahead moving and keeping that mode excited, just that. It is mixing. It is mixing everything. So it is coupling the modes just because of one single but important damper, all right? Then now, going ahead with the visual understanding of what is happening, we should work a little bit on the most relevant things that are happening. So the most relevant thing is that we must be very confident with what are doing those quantities. Those quantities are saying that the damper itself is effective, but just in case the location where it is positioning the force is not a nodal position. If I am positioning the damper into here, into a nodal location of one specific mode, at the node, if xj is the nodal location of a generic mode, is zero, this contribution. If in case I am positioning the damping in the antinodal location, is maximum the contribution. So if I want to be very effective with the application of the damper with respect to the first mode, I have to position in the middle. If for the third mode, in the middle. For the second mode, the damping in the middle doesn't make anything. It is hitting the location where phi2 is equal to 0, all right? But this is very simple, it's obvious, all right? So it is obvious, but is extremely important. So it's extremely important that we have the feeling that those functions here, positioned here, is not mathematics, it's something very, very practical. And so making the positioning a damper here in a location that is moving, yes, all right, but not too much. And then pretending that the motion is transferred into this direction. Where the movement is going into this direction, it means that this movement in this direction, all right, it will have a component, all right. It has a component, but it is very bad. So it is not very effective. So I will collect down here displacement that are very small compared to the actual displacement that we have here that is not the maximum. All right? This engineering way of looking at the quantities is the fundamental part. So we are dedicating all the time to the development of the theory in order to be aware, to be conscious about what we are doing. But then it is absolutely necessary that we are also capable of making these evaluations that are very practical engineering evaluation, where we understand into the structure what we are writing and in which way all of that is applied. Then So now, let's forget one moment that we have all those terms, but let's concentrate just on the S equation in where we are considering just the diagonal element, all right? So let's put our attention on the diagonal quantity. I would like to make clear in which way we are referring this quantity to what is very relevant for us, that is the non-dimensional damping. Because actually, the quantities that are relevant for us are the non-dimensional damping, not the dimensional damping. So when we have a system that is vibrating and having a trend like that, this trend is recognized being highly damped or not highly damped with respect to the quantity that is the non-dimensional damping. So we must be aware of in which way to link this quantity to the non-dimensional damping. So let's write all of that. So first of all, this quantity was written as Rj, the model shape, square at the location. Now, I have, the movement that we make, we divide everything by ms. So we divide everything by ms, all right? And so we are dividing this by ms star, all right? And this is equal to what? Oh, signore. No, I forget this. No, let's not consider this because it's late. I wanted to say something different. It is too late. It is too late. It takes too much time. So we spent a lot of time at the beginning with the question of the distributed load, and but I hope that this was a little bit clear, more than other things. And then those things that we are doing here takes 10 minutes, so it takes too long. So we stop here. We continue next time with the small things that are left. All right.